Hello and welcome to this seventh and last session with me of the massively open online course for the master's degree in digital currencies with the University of Nicosia. This is Andreas Antonopoulos, and I'll be answering your questions from last week's session. We're talking about alternative chains and alternative to Bitcoin. First, a quick check. Let's make sure everybody can hear me and see me well. If you could please let me know on the live chat and confirm that audio and video is good. We do have better bandwidth today. I'm in a different location, as you can tell from the background art. And very good. Excellent. Great. Everybody can hear me well, so let's get started. First question comes from Anastasios. Since Bitcoin is not efficiently used for micropayments, which was Satoshi's vision, is the concept failing? Why do we need second or third or fourth layers atop the Bitcoin blockchain to do what was supposed to be done by design? Should we move to other altcoins? And the follow-up question to that: how is Bitcoin's blockchain better than other algorithms like IOTA's, and why do we try to fix scalability issues instead of using other technologies? Is it just because of Bitcoin's huge adoption and miner support? Anastasios, this is an interesting question. One of the problems here is that when people talk about scalability, they tend to talk about it in isolation. So they talk about scalability as just one aspect of the system and optimizing scalability. And optimizing scalability is not difficult. Optimizing scalability of a network and allowing it to do millions of transactions per second on network, totally possible. It is very much possible. The problem is that in doing so, you sacrifice other parts of the design. So the way to increase scalability massively is to centralize the network. So if you have more centralization, you can achieve much more scale. Blockchains are particularly inefficient at doing things because they sacrifice scalability in order to achieve decentralization. And so if you decide to instead sacrifice decentralization, make the network more centralized, or aspects of the network, such as mining or clearing or exchanges or wallets or transaction processing, then you can massively increase the scale of the network quite easily, in fact. So, how do you achieve Visa scale network? Well, you can do it the way Visa does it, which is you have one validator, and that's Visa. And the problem with that model, however, is that when you have a centralized network like that, the central validator has enormous power. They have the power to censor transactions. They have the power to pick and choose transactions. They are a gatekeeper over the system. Bitcoin was designed to remove that central point of failure. So it chooses to maximize decentralization as much as possible. And in order to do that, it sacrifices scalability. Now, there's a lot of discussion about Satoshi's original vision. And, part of that, I feel, is a bit of appeal to authority. Satoshi, whether that was one person or a team of people, were only humans, and they had a very limited perspective on what this technology would ultimately become. We are now almost 10 years past that original vision, and a lot has changed. And we've also learned a lot about blockchains, about the scalability of blockchains, about the global competition in mining, and various other aspects of the system. And Satoshi, whoever they were, is just a human, not a prophet, not a saint, not a deity. They did not have a magic crystal ball with which to predict the future. And so while the original vision and design of Satoshi was remarkably prescient and had an enormous amount of things predicted correctly, that doesn't mean that everything Satoshi ever said is correct, or that everything Satoshi ever imagined Bitcoin would be is correct, achievable, desirable, or that Satoshi wouldn't change their mind when presented with new facts and evidence. For example, one of the pillars of Satoshi's vision was the idea of one CPU, one vote. The idea that the processing of transactions, the mining of transactions, would be done in a very decentralized fashion by a lot of different participants, allowing everyone who has a CPU to mine independently and have equal participation in the network. Now, that's not how it played out. In fact, if you read what Satoshi said, you can see that they were quite dismayed with the emergence of, and the very rapid emergence of specialized hardware and the move to application-specific integrated circuits, ASICs. And that caused enormous pressure for centralization of mining. So think about blockchains as trying to optimize across 3 different axes. And those are scalability, security, and decentralization. And part of the problem is that when you try to optimize one of those, it might be at the expense of the other 2. So the easiest way to maximize scalability is by damaging decentralization and security. It's actually very difficult to optimize without making a trade-off. So a lot of alternative blockchains propose that there is a simple and easy solution to scalability. Of course, what they don't reveal immediately is that that solution damages decentralization or damages security in some other way. And that's a trade-off that they may be willing to make. And that's an alternative approach to solving this problem. But it's not the trade-off that Bitcoin makes. Bitcoin prefers decentralization over scalability. And that means that in order to achieve scale while maintaining decentralization and the security model without reducing decentralization, you have to look at solutions that include second and third layers. So when somebody suggests that there is an easy and simple solution, if we only switch to this other alternative algorithm, alternative mining scheme, alternative consensus algorithm, alternative currency, alternative blockchain, and that blockchain has infinite scale or can achieve scale without any compromises, they're lying. You do have to make compromises, and often those compromises are brushed aside. So the question is not how do we achieve scale? The question is how do we achieve scale without sacrificing decentralization? Phil takes the exact opposite position in his question. Question from Phil. Bitcoin is making substantial progress in the areas of transaction speed with Lightning, privacy, CoinJoin and confidential transaction, and smart contracts, rootstock. Would I need to shift to altcoins then, which might represent a less decentralized technology? It's not clear, Phil. I would say, just as I said before, that there are no magic answers that solve all possible problems. I would say that also applies to Bitcoin. And so achieving speed of transaction, scalability with Lightning, achieving privacy with CoinJoin and confidential transactions, and achieving flexible, rich, expressive programming through smart contracts, it may not be possible to achieve all 3 of those goals simultaneously. And if that's not possible, then the question is, which of those is optimized on the currency or blockchain that you choose to use? And these are not always choices that don't have side effects. So maybe if you choose to have a blockchain that has a very flexible, rich, and expressive smart contracts language, maybe you can do that with the same level of security, robustness, censorship resistance as Bitcoin. I'm not persuaded that you can yet, and we'll have to find out. In every one of these cases, there are design trade-offs. This entire area is, like any other area of engineering, a matter of deciding which trade-offs are worth making. And that choice necessarily means that you don't get some of the other benefits of the other path you didn't choose. So if you choose to go down the path of flexible, rich, expressive smart contracts, you may necessarily close the door to certain aspects of security and robustness. You may create a larger attack surface or exposure. And you can't have both. I've talked about this extensively in one of my talks called The Lion and the Shark, which is about divergent evolution, the idea that you can be a top predator in one particular niche, but when you specialize in one niche, you choose that over others, and then you can't do both effectively. And so comparing different altchains that have made different design trade-offs, it's not possible to compare them directly against each other. It doesn't make much sense. The real question is not which is the best solution. The question is which is the best solution for my problem, and you have to first define the problem. Simon asks, do you think that a change in proof of work in Bitcoin will keep the network decentralized? Could the hashing be done via a different function, or would we have to change the whole algorithm to make the process of mining more accessible to a wider range of people without ASICs? Simon, I wish there was a simple answer to this. First of all, changing the hashing algorithm is almost impossible. And the reason it's almost impossible is because that change would have to be initiated primarily by miners who have an enormous investment in infrastructure and hardware. They would refuse to make that change. Alternatively, you could have the entire economic majority, that means everybody else except for the miners, make that change and force it on miners. But in that case, you're talking about a contentious hard fork that will likely split the currency into two. So you'd end up with two Bitcoins, Bitcoin SHA-256 and Bitcoin new algorithm, or whatever that may be called. And who knows which one would be more successful or have better security. Creating algorithms that are ASIC resistant is not easy. And eventually, all algorithms, I think, become susceptible to ASICs. Really, some algorithms, of course, are much easier to implement in an ASIC. Others are harder to implement in an ASIC, but they're not impossible to implement in an ASIC. Also, if you make something that's not susceptible to an ASIC, you're pushing the technology down to FPGA or GPU level computing, but you're not pushing it all the way down to CPU. So as long as you can use GPU optimizations, that still means having access to specialized hardware that is very difficult to get. As you know, probably, in the area of GPU mining, there's an enormous worldwide shortage of GPUs. Because of cryptocurrency mining that is affecting the gaming industry, and has created all kinds of controversy in gaming. So just because you make something ASIC resistant doesn't mean you can't mine it with a GPU. And a GPU is also specialized, difficult to get hardware that has a limited set of manufacturers. And when you have a lot of demand, can cause price spikes and shortages. So that doesn't really solve things. Finally, there are some significant advantages to having ASICs. ASICs really offer an important security guarantee, which is that because the ASIC is application specific and can't do anything else and can't be changed, that means that miners who use ASICs make a significant infrastructure investment, a capital expenditure, and commit to a specific cryptocurrency or a range of cryptocurrencies. So the miners who have bought SHA-256 ASICs have made an investment that they can only pay off if they continue to mine Bitcoin by following the rules. That is a very, very big part of the security guarantee of Bitcoin. Imagine, for example, if for whatever reason, Bitcoin decided to successfully switch algorithms and switch to something that was GPU mineable. Guess what happens next? If Bitcoin suddenly became mineable by GPU, and profitably so, that would cause an enormous exodus where all of the different cryptocurrencies that are currently mined by GPU would have their miners abandon that currency and switch to mining Bitcoin because it's more profitable. You can imagine the damage that would do to, for example, Ethereum, which is proof of work at the moment, perhaps if it wasn't going to proof of stake, or other cryptocurrencies that are proof of work and mineable on GPU, they would suddenly see their hash rate collapse. Part of the reason that Bitcoin's hash rate does not collapse in that way is because if you have SHA-256 ASICs, there are very few cryptocurrencies that you can mine profitably. And that means that the established infrastructure and capital expenditure the miners have made keeps them honest and keeps them competing for the security of Bitcoin. Finally, and this is really important to realize, cryptocurrencies that are easily mineable by GPU and CPU create massive botnets. People find it easier to compromise computers, family computers, grandma's computer, your aunt, uncle's computer, your cousin's computer, the computers running in web cafes, the computers running at airport kiosks, the computers that run printers, and all kinds of other computers like that, and use them to mine cryptocurrencies instead. Every now and then you hear in the news that somebody got arrested because they used their university computers to mine cryptocurrencies, or they used a company's computers to mine cryptocurrencies, or there's some kind of virus, worm, or Trojan that is hijacking browsers or phones or printers or network routers and using them to mine cryptocurrency. Very often those headlines say that they're mining Bitcoin, but that is always incorrect. They're not mining Bitcoin. And the reason they're not mining Bitcoin is because you can't mine Bitcoin on a CPU or GPU effectively. They are mining CPU and GPU capable cryptocurrencies. When you have CPU and GPU capable cryptocurrencies, then it is much cheaper to go and compromise somebody else's CPU and GPU and use it to mine than to buy your own. And that creates botnets. All right, quick check-in with the chat room. Let's see what's happening, if there are any follow-up questions, if everybody's paying attention and hearing everything. Very good. All good so far. Marcus asks, what are ERC20 tokens and how are the functionalities different to typical Ethereum tokens? They are not different. In fact, what you would call typical Ethereum tokens or Ethereum tokens are ERC20 tokens. 99.9% of them, I would guess. I haven't done a survey, but that's my rough guess, are ERC20 tokens. So you can write a token implementation as a smart contract in Ethereum in, I don't know, maybe 30 or 40 lines of code. And before the introduction of ERC20, plenty of people wrote smart contracts to implement tokens on top of Ethereum. What ERC20 does is it specifies a single standardized interface on how tokens can be used. And that interface has certain functions, such as transfer from, approve, balances, etc., that show you the internals of the contract or allow you to execute specific functions within the contract. And those functions take a specific set of parameters. So anyone can write an ERC20 token implementation as long as it has those functions with the same parameters so that a wallet can call them and get the result they expect. So ERC20 is a specification, it's a standard on the behavior of a token smart contract and its interface. So once ERC20 existed, then people started creating tokens using that standard so that all kinds of different wallets by different wallet implementation development teams would be able to access their tokens and use them and be compatible. And so that exchanges could easily list them and do withdrawals and transfers. So ERC20 is a standard, and that standard has proliferated, has become the de facto standard, and all Ethereum tokens nowadays are implemented with ERC20, even though it has a few weaknesses and glitches and quirks that people have to be very careful with. There are some competing standard proposals, such as ERC223 and ERC777. These are other standards for implementing tokens, slightly different interface implementations. Some of them are somewhat compatible with ERC20, some are not. Marcus asks, why would one use MetaMask or My Ether wallet or My Crypto? Is it just that they can hold multiple Ethereum-based tokens, or do they have more useful capabilities? Marcus, MetaMask, my Ethereum wallet, my Ether wallet, and my crypto are three lightweight clients and wallets. What they do is they don't just implement wallet functionality. They also expose to your browser or make available to your browser the Web3 JavaScript interface that allows dApps, decentralized applications, to run in your browser and access the Ethereum network through this wallet to create transactions, to access contracts, et cetera, et cetera. So these are more than just wallets. They're wallets and lightweight clients that can expose the application programming interface that allows a web application to access the Ethereum network. So yes, they can hold multiple Ethereum-based tokens, but they can also support web applications that access Ethereum. Pardon me 1 second. All right. Marcus asks, how could I issue a new token? Would I need to construct smart contracts? In which platform could I do that? Well, you can issue a new token on a variety of different platforms. But nowadays, most tokens are issued on Ethereum. The vast majority are issued on Ethereum because it's proven to be a flexible and convenient platform for issuing tokens, and because there are some standards that make it easier then for those tokens to be listed on exchanges and supported by wallets, specifically the ERC-20 standards we just talked about. You could also issue tokens on platforms running on top of Bitcoin, such as Counterparty and Omni. You could issue tokens on Rootstock, Ethereum Classic, Lisk, or any other EVM-based smart contracts platform. But for the most part, you'll see them being issued on top of Ethereum. Will you need to construct smart contracts? Yes and no. I mean, you could write your own smart contract, but you could also just use one of the existing reference implementations. They're probably better written, they're better tested, they're better audited, and more secure than anything you would write yourself. Generally speaking, when dealing with smart contracts, it's better to reuse something that's already been well tested than to try to write your own, unless you need something very specialized. And finally, Marcus asks, what is the difference between issuing ICOs and issuing a token? Are ICOs ERC-20 based? That's a great question, Marcus. So there's a lot of confusion between the term token and the term ICO. A token is basically an abstraction of value or access that can be used to convey certain privileges, rights, or ownership to someone. So, for example, a token can represent a share, it can represent a vote, it can represent access to a platform, it can represent the ownership of an asset. So tokens are these abstractions that are used to convey value, to express ownership, and do things like that. And most of those are based on the ERC-20 interface. Some of them are slightly different. For example, non-fungible tokens, such as CryptoKitties and deeds and asset ownership tokens, are actually based on a different standard than ERC-20. Off the top of my head, I believe it's ERC-721. But the bottom line is tokens are essentially the abstractions of ownership or access. An ICO is the means by which you sell these tokens, or one of the means by which you can sell these tokens. In the case of an ICO, that usually means selling these tokens to the public at large. So it's an initial coin offering. So you need a token in order to hold an ICO. But if you have a token, you don't have to hold an ICO. Instead of an ICO, which is a token sale, you could distribute tokens. You could allow people to mine them. You could distribute them in a way that everyone who already has another token or another coin gets one of these new tokens or coins, that's called an airdrop. You could use an auction. You could use all kinds of different mechanisms. So an ICO is one way to distribute tokens or sell tokens into the market. And really, for the most part, the reason we see so many tokens is because there are so many companies trying to do ICOs, because they find it to be an easier and faster way to raising money. And of course, a lot of them, perhaps the vast majority, are either outright scams or have very, very little to show for all of this fundraising. Perhaps among them there are some interesting things. We'll see how that works out. Unfortunately, this craze with ICOs has caused a lot of companies to create tokens when they don't actually need the token for their application, but they find it a convenient way to raise money. So a lot of the companies and startups that would otherwise go to a venture capital firm or get a loan from a bank or use another mechanism to fundraise use ICOs instead. And in order to do an ICO, they need a token. So they create a token, pretend it's a utility token for selling their product or service rather than a securities issuance, and then use an ICO to raise money. This will not end well for most of them. OK, checking back in with the chat room. Let's see how things are going. Simon asks, regarding Ethereum, what if there is a bug in the initial program running on all of these different machines? Is there a way to correct the code in the contract, or is it forever flawed? Simon, you've picked up on something that is a fundamental design consideration when designing smart contracts. Smart contracts are recorded on a blockchain, and they represent a fundamentally different development process, because once you create a smart contract and encode it on the blockchain, its code cannot change. It is immutable. It will forever run that way. This creates quite a problem, because if you have a bug, that means that that bug will be there forever. You cannot modify that contract after it's been created. Now, there are a few ways to get around that. One way to get around that is to essentially create a process where you can migrate from one contract to another, to another, to another, so that you essentially move all of the data, all of the tokens, all of the owners, all of the information that's stored within the contract to a new version of that contract that you deploy in the blockchain, and then you kill the old one. However, this isn't so easy to do either, because if you can migrate all of the data, all of the ownership information and all of that to a new contract, that means ultimately that the developers who deploy this contract have to retain control over it, which means it's not very autonomous and it's not very decentralized, because you have centralized control and the developers have to retain that control in order to be able to upgrade it. You have some potential issues there. That also means, of course, that there is a whole other class of bugs that can exist in the upgrade code. Specifically, if you look, for example, at the DAO, which is one of the most famous vulnerabilities in the Ethereum space. The DAO had a bug in the code that was meant to split the DAO so that people could fork off, potentially upgrade, and change the code. So there's a potential that the code that checks who the owner is and allows you to upgrade and migrate to a new contract itself can have bugs. And that's a whole other category of bugs. So this is one of the problems, not problems, it's one of the differences between developing software in a traditional centralized code release, code test release, and version upgrade mechanism, a classic software development methodology, and the methodology you have to use with smart contracts on a blockchain, where you don't have an opportunity always to fix mistakes from the past, or where creating the opportunity to fix mistakes is in itself quite complicated. Simon asks, do you think it's possible to combine smart contracts with AI and machine learning? Maybe, in very small ways, but not in any practical way and not anytime soon. These are both very mature, very new technologies. And when I say both, I mean smart contracts and AI and machine learning. And while they're progressing really, really fast, they're not necessarily easy to combine. So what happens if you take smart contracts and combine it with AI? Well, now you took all of the risks and problems of one immature technology, and you multiplied them by all of the risks and problems of another immature technology. It makes for a fantastic marketing brochure, and you'll probably raise a lot of venture capital money from investors who don't really understand what AI or smart contracts are, and are very impressed by these buzzwords. But the truth is that in practice, doing anything that involves two experimental technologies increases your risks exponentially. And I don't expect we're going to see any useful or practical or relevant, interesting applications combining AI and smart contracts in the next several years, perhaps even decade. Sudhakar asks, is the EVM, Ethereum wallet, and Mist the same thing? If not, what are the differences, and how do you install each? These are three different things. Mist is a user interface or dApp browser. So it is a front end that allows you to access and interface with decentralized application. And so a dApp browser like Mist is a wallet, a client, and a front-end user interface. So Mist is all three of those things. And there are a few others. Parity Wallet has its own graphical user interface and front end. My Ether Wallet and My Crypto are also in that category. Ethereum Wallet is one application that runs within Mist, which is just a simple wallet running as a decentralized application. It's really just a front end to a simple Ethereum wallet. And EVM, the Ethereum Virtual Machine, is it's a virtual machine that executes smart contract code that is being compiled into bytecode, which is a bit like a machine language. An EVM runs inside every Ethereum client and is used to validate every Ethereum transaction. It's also run by miners in order to validate transactions, and it's how smart contracts get executed. So Mist and Ethereum Wallet use a client. In the case of Mist, for example, they use the Go Ethereum client, or Geth. And that client has within it an EVM for validating transactions and executing smart contracts. So there is an EVM inside Geth, which is inside Mist. Perhaps that helps you understand some of the differences. Sudhakar asks, how is gas used? Is it used only in Ethereum? This is a very interesting question, Sudhakar. And gas is a fascinating topic when it comes to Ethereum and other smart contracts-based platforms. So when you hear people talk about Ethereum, a term you're going to hear almost immediately is the term Turing complete. And when you hear Turing complete, it sounds like something that is a great feature to have. I mean, after all, if you're not Turing complete, that means you're Turing incomplete, and that sounds like you're missing something. In fact, it's not the case. A Turing-complete language, such as the languages used in the smart contracts running on Ethereum or the Ethereum virtual machine, is one that can execute a program of arbitrary complexity. Usually that means the programming language has the ability to run loops. In fact, it's very easy to make something Turing-complete. Even very, very simple systems are Turing-complete. And in some cases, even systems that were not meant to be Turing-complete become accidentally Turing-complete and end up being far more flexible than originally thought. It's actually harder to make something Turing incomplete, meaning preventing it from executing all kinds of arbitrary code and keeping it constrained. And part of the reason for all of this has to do with a proof made by Alan Turing in 1936, which was the halting problem, or Entscheidungs problem, where Alan Turing proved that if you have a Turing-complete system, you cannot predict whether that system will ever stop running or whether it will simply run forever. You also can't predict if it will follow a specific execution path or execute a specific part of the code. And this causes a significant problem because with a smart contract that's running in the Ethereum virtual machine, every single Ethereum client that's participating on the network has to validate that program by running it. Now, how does it know how long that program will run? Can the Ethereum client predict how long a program will run and whether it will consume a certain amount of resources? And what Turing proved back in 1936 is that you cannot predict that. And therefore, Ethereum doesn't have any way to know if a program, based on some starting conditions, like a specific input from a transaction in the blockchain as it is at the time of execution, will run for a second, 1,000 seconds, 1,000,000 seconds, or infinity. It doesn't know if it will execute 1 command, 10 commands, 1,000,000 commands, or infinity commands, never stopping and going into an infinite loop. So if your Ethereum client has to run a program in order to validate it, how do you make sure that these programs do not consume all of the resources of all of the computers participating in Ethereum? Vitalik Buterin's solution to this was to make the language of Ethereum Turing-complete, so as to give maximum flexibility, but then add a way to constrain it so that it didn't consume resources without end. And that mechanism is gas. So gas is a way of prepaying for a specific amount of execution or resources for every computer that will validate it. And every transaction in Ethereum provides an upper limit on the amount of gas that that execution will be able to consume. And when the smart contract is executed by the Ethereum virtual machine, the Ethereum virtual machine starts accounting for gas by essentially debiting an amount of gas for every instruction executed by the smart contract. And if, during this process, the smart contract runs out of the available gas in the transaction, it stops it. So it forces it to have an upper limit on how much execution, how much resource can be consumed by any smart contract. There's also a gas limit for every block, which ensures that no matter how many transactions are in a block, there is an upper limit on the maximum amount of computation and resources consumed to validate and execute that block. And so that's the role of gas. Gas is the solution to the problem introduced by the extra flexibility of a Turing-complete language that, as a result, has no ability of predicting how long a program will run and could create conditions where a single transaction takes forever to validate and locks up all of the processing of all of the computers participating in Ethereum. Isa asks, can anyone create their own coins using Ethereum? Yes, you can create your own, and those are called tokens. In last week's class, we talked about the difference between coins and tokens. And while this isn't a broadly accepted definition, I use it for convenience. Coins are things that have their own blockchain. Tokens are abstractions that run on top of another blockchain. So ERC20 tokens or Ethereum tokens are abstractions that run on top of the Ethereum system, which has its own coin called Ether, which runs on its own blockchain, the Ethereum blockchain. Similarly, you could have Bitcoin with its own coin, which is Bitcoin, which runs on its own blockchain, Bitcoin, but it also has the ability to run tokens, such as those built using Counterparty or Omni. And those are not coins. They don't have their own blockchain. Isa asks a follow-up question. How was Ripple and Litecoin created? So both Ripple and Litecoin have their own blockchain. So they are independent coins. They're not tokens running on top of another blockchain. And they have a very different path. Litecoin is based primarily on Bitcoin's code base. So Litecoin is a slight modification of Bitcoin's code base and has been following the development of Bitcoin very, very closely. It's meant to be a lighter, faster version of Bitcoin, exploring some different trade-offs between scalability, security, and centralization. But it still maintains more than 99% the same code base as Bitcoin and keeps upgrading accordingly. Ripple, on the other hand, is a completely separate code base. It has nothing to do with the code in Bitcoin. It has a different model for implementing its network. It has a different model for validation of transactions. It uses a federated model instead of a blockchain. And it has different properties for security, decentralization, and scalability. Rule asks, where are Ethereum transactions stored after executing the contract code? That's a really great question, Rule. So Ethereum transactions are stored on the blockchain the same way that Bitcoin transactions are stored on the blockchain. The difference is that where Bitcoin transactions track the state of ownership of specific coins, or unspent transaction outputs, as they're called, in Ethereum, the transactions may trigger smart contract execution, and that can modify the state of a contract or the state of an account within Ethereum. So Ethereum transactions track or cause changes or state transitions in any form of state that could be data within a contract or the balance of an account, a much broader set of state. What's actually stored in the Ethereum blockchain are two things. The first thing is the transaction itself. And the second thing is the transaction logs, or receipts as they're called, which show what changes this transaction caused to the global state. The contract execution itself isn't stored on the blockchain. So you store what started the contract, and you store what state changes happened because of the execution of the contract, but the execution of the contract itself is not stored on the blockchain. You essentially store the inputs of contracts, which are transactions, and the outputs of contracts, which are state changes. Those are the two things that are stored on the Ethereum blockchain. And so anyone can validate this information by taking that same transaction that's stored on the blockchain, playing it through the smart contract execution by running it on the Ethereum virtual machine, and then looking at the output of the Ethereum virtual machine, the logs, and seeing what state transitions occurred during the execution of the smart contract and what state changes occurred, and comparing those with the receipts or logs that are stored in the Ethereum blockchain. Every single validating node on Ethereum should arrive at exactly the same answer. The same transaction should cause the same state changes and produce the same receipts and logs. And that's how Ethereum validation is done. Sudhakar asks, what will Metropolis mean for Ethereum? Great question, Sudhakar. So Metropolis is the third out of the four planned transitions for Ethereum. Ethereum was deployed in a manner that expects that there will be certain major transitions between different stages of development. The first stage of development for Ethereum was called Frontier. And Frontier was the stage of development that involved the pre-sale of Ethereum and the first, essentially, pre-beta version of Ethereum that ran on the network. The current version of Ethereum, or the current stage of Ethereum that we're running today, is called Homestead. Homestead is planned to end in the next year, and will transition to the third stage of Ethereum called Metropolis. It's also predicted and named in advance that the final stage of Ethereum, which will be the stage that Ethereum settles in, if you like, will be called Serenity. So Frontier, Homestead, Metropolis, and Serenity are the 4 evolutionary stages of Ethereum. Metropolis was actually planned for 2017 or perhaps the end of 2016, but because of the DAO incident, the fork to Classic, several denial of service attacks, and other problems that occurred during Homestead, instead, the developers were delayed and distracted, fixing security problems and doing a number of hard forks to address certain vulnerabilities discovered in Homestead. As a result, Metropolis has been delayed, but it is expected in 2018, and it is moving pretty fast now. Metropolis introduces a number of different changes to Ethereum, and it's going to happen in 2 stages, which are codenamed Byzantium and Constantinople. Byzantium is the first stage of Metropolis, and Constantinople is the second stage of Metropolis. Each of those will be a hard fork, or perhaps more than one hard fork, that will introduce a number of changes into the Ethereum system. A couple of big things that are happening, specifically for Byzantium, which is stage 1 of Metropolis, are the introduction of ZK snarks, which allows Ethereum to be able to use the technology introduced by Zcash to do zero-knowledge transactions for very, very high levels of confidentiality and privacy. ZK snarks and native execution of ZK snarks has been a goal of Vitalik Buterin's for a while now, and it will be introduced with Byzantium. The other very big change introduced with the first stage of Metropolis is the move towards proof of stake. So today, Ethereum operates using a proof of work, a mining algorithm called ET hash or ETH hash. ETH hash is a mining protocol that uses hashing with the SHA-3 Keccak-256 algorithm, similar to how Bitcoin does mining with SHA-256, with a few changes that make it a bit more memory intensive to prevent the easy development of ASICs. In the first stage of Metropolis, Byzantium, a new mechanism will be introduced, which is proof of stake. And proof of stake will be using a protocol called Casper. Proof of stake is different from proof of work in that it allows validation of transactions without mining, instead using validators who stake or bet an amount of Ether in the validation of a block. And if they validate a block that is broadly accepted by the network, they receive a small reward in proportion to the amount of stake that they bet on the validation of that block. And if they approve a block that the rest of the network rejects, then they lose their stake. And so this mechanism of reward and punishment is different than the mechanism of mining that requires computation with repeated hashing, and is going to be introduced with Byzantium. Ethereum is not going to move directly to proof of stake. Instead, in the first stage, it's going to move to a hybrid environment where it uses proof of work and proof of stake simultaneously. Another big change that's coming with Byzantium is the diffusing of the difficulty bomb. Ethereum had a planned system within it called the difficulty bomb that was intended to force the developers to move to proof of stake by making it increasingly difficult to mine using proof of work. That difficulty bomb is expected to increase the validation of blocks from every 14 seconds to more than 15 seconds in the next 3 months, and then within 6 months to 28 seconds or more, and then quickly exponentially increase the difficulty until it is impossible to mine transactions on Ethereum. Now, that's obviously not ideal, because due to the delays in the deployment of Metropolis, now the difficulty bomb is upon us. And so one of the first changes that happens with Byzantium is pushing back the imposed difficulty that the difficulty bomb creates to give more time to deploy proof of stake. A couple of other really interesting developments in Metropolis and Byzantium are the introduction of account abstractions, where gradually Ethereum is moving to blur the line between the 2 account types that are available. At the moment, Ethereum has 2 types of accounts. There are externally owned accounts, or EOAs, which are accounts that are owned by systems outside of Ethereum with private-public key pairs. Wallets, for example, in Ethereum are externally owned accounts. And contracts. Contracts are the other type of account where money is managed by the code executed by a smart contract. They have some differences between them, and the way they're validated is different. The way they pay for gas is different. And these differences are going to gradually be abstracted so that they behave more and more the same until eventually Ethereum only has one type of account. And there's no difference between an account that has a private key behind it or some other mechanism for authorization or signing, and an account that's managed by smart contract code. They will behave identically. Another big change is the introduction of the ability for intermediary accounts to pay for gas. So today, if you run a transaction that executes smart contract code, that transaction has to pay for the gas. The smart contract itself can't pay for the gas. And if the smart contract calls another smart contract, which calls another smart contract, which calls another smart contract, then the gas is still paid by the first transaction that initiated this chain of calls. With Byzantium, the intention is to allow intermediate contracts to pay for gas themselves. So you can call a contract with a transaction, and then when that contract calls another contract, it can pay for all or some of that gas. I think that includes most of the changes we'll see in Byzantium, but of course it's still in flux, and there may be more changes introduced in Byzantium, or maybe some of the changes will be pushed back into Constantinople for the second part of the metropolis upgrade. And I think that covers a lot of the questions that we had here. Let me see if I have one more. Quick check in the chat room, see how things are going. Great question. As a follow-up to some of the questions I answered about gas and execution, Winter Matiko asks, Andreas, can you please explain how can I, as a smart contract developer, be able to know how much the execution of my program will cost on the blockchain? That's a great question. I have a difficult answer for you, and maybe you won't like this. It is not possible to guess how much gas the execution of a contract can use. In fact, Turing proved that even long before stored program computers existed, smart contracts and blockchains existed. He proved that it's not possible to predict whether a certain execution path will be executed by a program other than running it. And in running it, you never know what's going to happen. So you can estimate the amount of gas that is used by a smart contract, but you can never predict it accurately because the conditions under which it runs may change between your estimate and what actually happens. Let me give you a silly, contrived example that shows how this works. Let's say I write a smart contract that has a counter in it, and if every time you call it with a transaction, it increases this counter, and the first 99 times you call it, all it does is 1 + 1 = 2. It does a simple addition. And that's going to cost a certain amount of gas. Let's say that costs 400 units of gas to run. It's a simple addition. But it looks, in that contract, it looks at how many times it's being called, and on the 100th time, it decides to do something else. On the 100th time, it decides to run a hash function 1 million times. Now, that's going to cost you, I don't know, let's say 5 million gas. So the difference between the 99 times you run this contract and it only consumes 500 gas, and the 100th time you run the contract when it consumes 5 million gas is simply the order of transactions. And it's very simple to create contracts like that. It's also very simple to accidentally create contracts where the amount of gas that's used varies considerably between one execution and the next based on circumstances that you can't predict. Let's say, for example, that you estimate the amount of gas that's going to be used to call this contract, and your software estimates this based on you being the 98th transaction in a row. And as you transmit your transaction, two other transactions first call that contract. And that means your transaction is now the 100th transaction in a row. And instead of costing 500 gas, it costs 5 million gas to run your transaction. And so you can't predict how the conditions will change until you actually run your transaction and it's included in the block, because the transaction just before yours may change the state of the contract in such a way as to cause it to follow a completely different execution path, to call other contracts, who knows what they're going to do, and to use gas in a completely unpredictable way. So this is one of the challenges with writing smart contracts, and actually the ability to have the contract pay for the gas gives us a bit more flexibility in how to plan gas expenditure and estimates for smart contract developers. Very good. I think that covers everything we had for this session. Thank you so much. This is the last session I'll be doing for the massive open online course for the University of Nicosia's master's degree in digital currencies for this semester. I'll see you again during the summer semester for 7 more exciting sessions, and good luck with the rest of your studies. I hope you enjoyed this course. I hope you continue to enjoy the course. We have several more sessions with Professor Polomitis, and for those of you who continue to do the master's degree, good luck with your studies. I wish you the best and quick graduation. Thank you so much for listening to me and for the many excellent questions you've been asking online. Have a wonderful weekend. Bye-bye.